Earlier this year the first detection of gravitational waves was reported, a discovery that was hailed the biggest scientific breakthrough of the century. A second detection followed a few months later, and scientists expect the next time the detector searches it could even find hundreds of events like black hole mergers that create ripples in spacetime. But a new invention could make the Ligo detector 10 times more sensitive, using X-rays to study mirror coatings, and this could lead to a new era of gravitational wave physics. Scientists from Stanford University and the Department of Energy's National Accelerator Laboratory have been studying the structure of the mirror coatings using X-rays. The detection of gravitational waves will fundamentally change our understanding of the universe in years to come, said Dr. Riccardo Bassiri, a physical science research associate at Stanford. Extremely precise mirrors are the heart of LIGO, and their coatings determine the experiment's sensitivity, or ability to measure gravitational waves. So improving those coatings will make future generations of the experiment even more powerful. LIGO consists of two nearly identical instruments, located 1,900 miles apart in Hanford, Washington, and Livingston, Louisiana. Because the distances involved are so large, tiny changes in the mirrors have a big effect. The effects of gravitational waves on the LIGO detectors are incredibly small, with relative changes in arm length on the order of 1,000th of the diameter of an atomic nucleus, Dr. Bassiri said. On this scale, random atomic motions in the mirror coatings, known as thermal noise, can obscure signals from gravitational waves. The materials used to coat the mirrors used in the LIGO detector, like tantalum pentoxide, or tantala, are among the least noisy in the world. Some processes are known to reduce noise in these materials, but exactly why is not fully understood. At the moment, we're only beginning to understand how these treatments affect the atomic structure, Apurva Mehta, a staff scientist at Stanford synchrotron radiation light source said. If we were able to get a better grasp of how a material's properties are linked to its structure, we might be able to design better materials in a more efficient, controlled way instead of searching for them with a trial-and-error approach. The researchers are testing various materials to see how different treatments affect the noise. They are looking deep into the atomic structure of the materials, to gain an understanding of how tweaks in the structures could lead to better properties. Advanced LIGO and the desire to understand the fundamental physics of gravitational waves are the main drivers for this type of research, Dr. Bassiri said. But it also has the potential for influencing a whole industry that uses amorphous coating materials for a wide range of applications, from precise atomic clocks to high-performance electronics and computing to corrosion-resistant coatings.